guys, today we're going to do 7-1, exploring exponential models. So you will be able to model exponential growth and decay. And our essential understanding is you can represent repeated multiplication with a function in the form y is equal to a times b to the x power, where b is a positive number other than 1. So first, exponential function. Our exponential function is, in general form, is y is equal to a times b to the x power. A cannot equal 0, b needs to be greater than 0, and b cannot be equal to 1. B is our base, and that is a constant. X is our exponent, and that is a variable with the domain of all real numbers. So x can be any real number. Problem 1. Graphing an exponential function. We want to graph y is equal to 2 to the x power. So we are going to make a table of values. I'm going from -4 to +3, and I'm going to plug in -4 for x. So we have 2 to the -4th power, which is 1 over 2 to the 4th power, which is equal to 1/16. 2 to the -3rd power is 1 over 8. 2 to the -2nd is 1 over 4. 2 to the -1st is 1/2. 2 to the 0 power, anything to the 0 power is 1. 2 to the 1st power is 2. 2 to the 2nd power is 4. And 2 to the 3rd power is 8. We then have to plot and connect our points. So we have -4, 1/16. So that's really close to the x-axis. Then -3, 1/8. So that's still really close to the x-axis. -2, 1/4. Please see how each time we move over an x value, we're just getting a little bit higher. Then we are going to -1, 1/2. Then we are at -0, 1, 1, 2, 2, 4, and 3, 8. We connect with a curve and arrows at both sides. So as we're going to the left, we are getting infinitely closer to our x-axis, which is called an asymptote. And as we are going to the right, or our x values are getting bigger, we are exponentially growing. So we have two different types of exponential behavior: exponential growth and exponential decay. You could see the blue graph is exponential growth because as we are getting, our x values are getting bigger, our y values are getting bigger. And exponential decay is our red graph, where our y values are getting smaller as our x values are getting bigger. So the exponential functions here have an asymptote at the x-axis. So an asymptote is a line that a graph approaches as x or y increases in absolute value. So as we are getting bigger, we need to be approaching this line. We're never actually going to touch or cross this line, which is our asymptote. So how do we know if we are going to have an exponential growth or an exponential decay graph? So if a is greater than 0 and b, our base, is greater than 1, we will be exponentially growing. If a is greater than 0 and b is between 0 and 1, so that means it's a decimal or a fraction, we will be representing exponential decay. either way, our y-intercept is 0, a. So a would be our constant. The domain is all real numbers. And our asymptote is y equals 0. So that means it's a horizontal line on our x-axis. Our range would be greater than our asymptote. So we could be greater than 0. It's not greater than or equal to because we never actually touch our asymptote. Did I skip too many? Okay, so we are going to identify exponential growth and decay. We have to identify each function as growth or decay and what the y-intercept is. So remember what we just had right here. And if our base is between 0 and 1, we are decaying. So this would be decay. A is our y-intercept. So our y-intercept would be 0, 12. For B, our base is 2, therefore it is growth. A is our y-intercept, therefore our y-intercept is 0, 0.25. For exponential growth, y is equal to a times b to the x power with b greater than 1. The value b is our growth factor. A quantity that exhibits exponential growth increases by a constant percentage each time period. The percentage increase r, written as a decimal, is the rate of increase or growth rate. For exponential growth, b is equal to 1 plus r. For exponential decay, between 0 is less than b, which is less than 1, or b is between 0 and 1. B is our decay factor, just like it was our growth factor. The quantity decreases by a constant percentage each time period. So the percentage decrease, r, is the rate of decay, which would usually, rate of decay is expressed as a negative quantity. So we would have, so b is equal to 1 plus r. So we need to keep in mind exponential growth and decay. We can model exponential growth or decay with this function. A of t is equal to a times 1 plus r t. A would be the amount of time after t time periods. A would be our initial amount. Rate of growth would be r, or rate of decay. If r is positive, then it would be growth. If r is negative, it is decay. And t would be number of time periods. So you invest $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? Remember, a of t is equal to a times 1 plus r to the t power. Determine if an exponential function is a reasonable model. Since we are growing at a fixed rate of 5% per year, an exponential model is appropriate. So yes. We have to define our variables. So let t equal years since 6th grade. And let A of t equal the amount after each year, so that we have our model. We can use our function A of t is equal to A times 1 plus r to the t power. So let's plug in what we know. We're trying to find A of, after 6 years, 6, is equal to our initial amount, 1,000, times 1 plus our rate is 5%. If our rate is 5%, we're going to transform our percent into a decimal. So we're going to move it over 2 places. So plus 0.05 to the 6th power. You can plug that into your calculator, and we would get 1,000 times 1.05 to the 6th power, and we get A of 6 is equal to $1,340.10. I'm sorry. Suppose you invest $1,000 in a savings account that pays $5,000 annual interest. If you make no additional deposits or withdrawals, how many years will it take for the account to grow at least 1,000 to at least 1,500? So think about the equation we have. We know that A of t is equal to our initial amount times 1 plus our rate raised to the t power. So we want A of t to be equal to 1,500, where our initial amount was 1,000 times 1 point. We want a decimal, 0.05, raised to the t power. We can divide by 1,000. Since we do not know how to do this just yet, we could put it into our graphing calculator, and I will show you that tomorrow in class. Writing an exponential function. The table shows, sorry I didn't put the table in there, the world population of Iberian lynx in 2003 and 2004. If this trend continues, and the population is decreasing exponentially, how many will there be in 2014? So, year 2003, 2004, 150, and 120. So, let x be equal to the number of years since 2003, y equal the population. We want to find out what r is, so think about y is equal to a times 1 plus r to the t power, or to the x power, I'm sorry. So we can use the populations for 2003 and 2004 to find r. So we would have 120 minus 150 over 150 to find our percent decrease, which is equal to -0.2. So we're going to plug that in.